Hello everyone, I am Dr. Sanket Sanghai from Department of Civil Engineering in GH Raisoni College of Engineering, Nagpur. Today I am going to cover an introductory topic on structural dynamics. So my presentation has following contents: what we have learned till date, why to learn dynamics, what is the difference between dynamics and statics, what is meant by degrees of freedom, and in the end we will try to cover modeling of the structures. So let us start with what we have learned till date. So basically structural engineering is divided into two different areas. One is subjects related to analysis and second is subject related to design. So in structural analysis we have learned these many subjects in our UG program, like engineering mechanics, strength of material, or which is also known as mechanics of material, structural analysis 1, structural analysis 2, or in many universities it is also called as theory of structures 1 and 2. Then we have learned matrix methods of structural analysis, and then we have learned a subject known as advanced structural analysis. So after learning so many subjects related to analysis, why we want to learn another subject related to dynamics, which is also an analysis subject now. So let us see what we have learned in various subjects first, and then we will come to know that why there is a need to learn this new subject. So in first year, if you remember, you have learned a subject engineering mechanics. So in engineering mechanics, what was our assumption? Our assumption was every body is a rigid body, and as you can see the figure, you must be recalling the things that you have learned in this subject. We have tried to find out the reactions of the beam, we have tried to find out various forces in the members, we have tried to find out basically what is the reaction developed when you apply any kind of force on your material. So the basic assumption in the engineering mechanics was every object is a rigid object, so whatever amount of force you are applying on that object, you are going to get some reactions, right? So after learning engineering mechanics, in second year we have started to learn strength of materials, right? In strength of materials we basically try to understand what is happening to the material of the various structural element. Means we have tried to understand what are the amount of stresses developed in that material, what are the amount of strains that are developed in the material. So the basic assumption was every material is deformable material, and we have tried to understand whenever you are applying the force on that member, what is happening to the material of that member. So that is what we have learned in strength of material. Also we have learned to analyze the determinate structures, right, in the strength of material, but analyzing the determinate structure was not sufficient. So in structural analysis we have tried to analyze various indeterminate structures like beams, frames, trusses, right? So for analyzing these structures we have learned various methods like three movement theorem, moment distribution method, Kani's method, strain energy method, but there was one lacuna of all these methods. If you are learning three movement theorem, then you cannot analyze frames or trusses using three movement theorem, you can only analyze beams. If you are using moment distribution method, you can analyze beams and frames, but you cannot analyze trusses. So there was a need of a common method which we can use to analyze all kind of structures. Also along with the common method we want a programmable method, because nowadays people are using various softwares to do the analysis of structure. So we want a programmable method. So that is why in next set of subject we learn matrix analysis of structure, in which we have tried to analyze the structure using matrix methods. We have prepared the stiffness matrix of the structure, then we have prepared the displacement vector, we have prepared the force vector, and then we try to solve those matrix to get the reactions or the shear forces, bending moment developed in those members. So after learning all these subjects, today I am going to tell you that there is a need of another subject which is called as structural dynamics. So what is the necessity of this structural dynamics? Because if you look at all these subjects, no, one thing is common. What is that one thing? In all the subject your force was stationary, the value of magnitude of that force was constant. So even if you are applying a point load, the value of that point load was constant. Even if you are doing the analysis for uniformly distributed load, the magnitude of that uniformly distributed load was constant. So if the force is varying with respect to time, then how to analyze your structure for this time varying force? This is the thing that we have not learned in all these subjects, and there comes the need of structural dynamics, right? So why to learn the dynamics? Because the quantification of dynamic forces. If your force is varying with respect to time, then you should be able to analyze your structure for these time varying forces. So what are the examples of the dynamic load? You must have experienced the wind load. If you go to the terrace of your building, you will feel the wind, right? And you can feel that variation in the wind. Wind is not constant for the entire duration of time. The force applied because of the wind changes with respect to time, right? So if you want to analyze your building, or if you want to analyze your structure for the wind load which is varying with respect to time, you cannot do by the methods that you have learned up till date, right? So that is why you need to learn the dynamics. So what are the other examples of time varying forces? Vehicular load. If you consider a bridge, the load on the bridge continuously varies. And then blast load. Blast load is a kind of load which is suddenly applied on the building. So very huge amount of load acts on very short duration of time. So these kind of loads are also considered as time varying forces. And another very popular load which is called as earthquake load, right? So if you want to do the seismic analysis of your building, or if you want to design your building for earthquake forces, then you have to first learn the dynamics, right? You have to learn the structural dynamics. Other examples of slowly varying loads are thermal loads, because there is always a change in temperature. So due to change in temperature, expansion and contraction is continuously going on, but this variation is quite slower. So we generally do not consider these loads as an time varying force, because the variation is quite slow. Similarly, live loads. So live load also changes, but the change is very gradual. So that is why we do not consider these loads as an time varying force. Now the next question arises, so even if the force is varying with respect to time, why just we don't consider the maximum value of load into the analysis, right? So look at the figure. The figure shows one force which is varying with respect to time. So what will happen if I only consider the maximum amount of load and do the analysis as per the method that we have learned till date? So what will happen? Let us try to see. Right. So why we don't consider just maximum load for the analysis? Because of the Newton's second law of motion. Everyone is aware about the Newton's second law of motion. What is it said? It says that force is equal to mass into acceleration. So if your body is moving with certain acceleration, so it will continue its motion until and unless it is disturbed by some another force. So in short, Newton's second law of motion says that force is equal to mass into acceleration. So if your force is varying with respect to time, then it is going to impart acceleration into your body, and when acceleration will come into picture, an additional inertia force will develop in your body, and this additional inertia force will change the way we look at the structure, right? So in static analysis, nowhere we have considered the inertia force developed in the body, because the force was statically applied. The force was gradually increasing. So if the force is gradually increasing, then it means that it is not going to impart acceleration in your structure. But if the force is suddenly applied, or if it is varying with respect to time, right, if it is changing abruptly, then it is going to impart acceleration into your structure, and this acceleration is going to introduce another inertia force into the body, and this inertia force should be considered in the analysis, and that is why we have to learn the structural dynamics. So this dynamic response is basically due to the inertia force, which is calculated as force is equal to mass into acceleration. So let us try to understand this inertia force by an example of a simple block resting on a surface. So look at the figure. We are having a simple block with weight is equal to 1000 kilonewton, and let us say we want to move that block. So I will apply the force P. When the block will start to move, when it will recover the frictional force offered by the surface. So let us say mu is the coefficient of friction, which is 0.2. So when your P will be greater than the R, then this block will start to move. So if we consider this case as a static case, because your block is stationary, then we can say that the P is equals to R. P is equals to R. How you calculate the R? Mu into W, which is the sulfate of your block. So now let us say that this block is moving with some uniform acceleration, right? So what will be our equation of when we apply the equilibrium condition, what we will get? Along with P and R, we will get an additional inertia force into the consideration, and that additional inertia force is nothing but mass into acceleration. So this acceleration which has imparted in the body has changed the entire game, and it has changed the way of analyzing the structure, and now your equation will become P is equal to R plus ma, right? Look at this picture now. This picture is showing a person moving on a vehicle. What has happened to him, right? When he hit that tires, he did not stop there, right? Though the vehicle stopped at that point, he did not stop there. Why? Because he was moving with certain velocity, he was moving with certain acceleration. So what has happened to him? An object in motion will remain in motion unless and until it is acted upon by an external force. So due to the inertia force into his body, he has thrown over the tires, right? So this is the impact of inertia forces, and try to understand that when the earthquake forces will act on your building, how much amount of inertia force will develop into your building, because what is the inertia force? Mass into acceleration. Try to calculate the weight of your building, try to convert it into mass, and then try to assume that if the some amount of acceleration is induced in your body, what amount of inertia force will develop. So you cannot definitely neglect this inertia force into the analysis, and that is why we have to learn the structural dynamics. Now to calculate the inertia force, there is a principle which is called as D'Alembert's principle. So let us try to understand what is the D'Alembert's principle, right? So the example of accelerating body can be considered as equilibrium problem, right? So the previous photo that you have seen, we can consider it as an equilibrium problem, but as it is moving, we have to call it as a state of equilibrium. Can be referred as dynamic equilibrium, right? In UG you must have learned static equilibrium conditions, because your structure was stationary, the forces acting on the structure were stationary, so we used to call that as static equilibrium. But now your structure is moving, your structure is vibrating, right, and your structure is dynamic, so that is why we are going to call this equilibrium as dynamic equilibrium, right? So in dynamic equilibrium, P minus R minus ma is equal to 0. So when we consider this case as a static equilibrium, we get external force is equal to the reacting force. But when it is a case of dynamic equilibrium, along with P and R, we have an additional force which is called as inertia force minus ma, which is opposite to the direction of motion, and that is what is stated in the D'Alembert's principle, right? So it means that in addition to the real forces acting on a body, a fictitious force of magnitude minus ma is acting opposite to the line and direction of motion. So this additional force minus ma you have to consider in the dynamic equilibrium, and this additional force, the inclusion of this additional force is nothing but the D'Alembert's principle, right? Next, what is the difference between dynamics and statics? So we have seen that dynamic analysis means a analysis which we are doing for the time varying forces, right? So when we consider the static response, in a static response time is invariant, because we know that force is constant, it is constant for entire duration of time, so time is not considered in the static analysis. Another thing is, it is governed by the stiffness of structure. So when you are applying a force, it is getting deformed. It is getting deformed because of the stiffness of structure. Stiffness will resist it, and the entire deflection will be governed by only and only stiffness of structure. So this is how you can represent a simple static analysis. A fixed support connected with the stiffness spring of stiffness K. This K will represent the stiffness of your structure, and when I apply a force on it, it will get deformed. So what will be the magnitude of force? K into x. Or what will be the displacement? F upon K. So in short, when you go for the static analysis, the response will be governed by only the stiffness of structure. But if you are going for a dynamic analysis, so now you know that my force is varying with respect to time. So if force is varying with respect to time, it means that you are not going to get a single value of displacement. Your displacement will also vary with respect to time, because the force which is acting on your structure, it is also varying with respect to time. So time is a variant in the dynamic analysis. Similarly, along with the stiffness of structure, inertial forces will also come into picture. So your response will be governed by not only the stiffness of structure but also the inertial forces developed in the structure due to the imparted acceleration. So now your dynamic analysis can be represented by this simple figure, which is having a spring which is showing the stiffness of structure and which is having an additional element mass which is showing the mass of your structure. So the displacement will be taken care by the stiffness, while the imparting acceleration will be taken care by the mass of the structure, and your dynamic equilibrium will be written as m into x double dot plus kx is equal to 0, where x double dot is nothing but d2x by dt square, the differentiation of displacement, double differentiation of displacement with respect to time, right, or acceleration. So this is the basic difference between the dynamic analysis and static analysis, right. So if we go further, we can see that in reality no load is actually a constant force. Even if you want to apply a force on any object, it is going to vary with respect to time, right, but that variation might be gradual or it might be sudden. So if that variation is gradual, right, then there is no need to consider that load as a dynamic load. What is the reason? Because the loads are applied during a finite period of time, and if that load is not creating acceleration, then it means that the inertia force developed in your structure will be negligible, because inertia force is equal to mass into acceleration. If the value of acceleration is smaller, then the value of inertia force will also be smaller, and in that case there is no need to go for the dynamic analysis of structure. We can correlate this thing with the experiments that you have performed in strength of materials lab. So if you remember, you must have performed the tensile test, right. So in tensile test, you have applied a tensile load on the bar, right. So if you remember that load was increased gradually, right. We were increasing the load from 0 to certain amount, right, 0 to 10, then 10 to 20, 20 to 30 during a some stipulated amount of time. So in that case, you can consider that tension test as a static test, right. You are applying the load statically. Similarly, in the same strength of materials lab, we have performed another experiment, that is impact test, right. So in that impact test, what we have done, we have placed the same mild steel specimen, we have released the hammer from certain height, and that hammer strike to your specimen with certain speed. So a huge amount of force was acting on that specimen for a very short duration of time. So what is the difference? In first case, you have increased the load gradually. So due to the gradual increase of load, the acceleration was not imparted in your specimen. But in the second case, in your impact test, the load was suddenly applied. So due to suddenly applied load, the acceleration was imparted in your specimen. So it means that if your load is gradually increasing, then the acceleration will be 0. So the inertial force in your equation of motion will be 0. So you can consider that case as a static load of analysis, right. But if the value of acceleration is more, then in that case you have to consider the inertial forces into acceleration, and that problem will be a dynamic problem, right. So the general question arises, when do we opt for the dynamic analysis? So when the forces changes with the time, if your force is changing with respect to time, then should we do the analysis? No, it is not necessary that every time if your force is changing with respect to time, you should go for the dynamic analysis. It is not at all necessary. If that variation is what we can say gradual, then there is no need, but that variation of force within the certain duration of time is very smaller, right. So if a huge amount of force is acting within a short duration of time, then you should go for the dynamic analysis. Again, why we do not do the dynamic analysis always? Because we have seen that every force is varying with respect to time. Then if it is the case, Why we just don't learn the dynamic analysis? The reason is very simple. Dynamic analysis is considerably more expensive than the static analysis. I am not saying in terms of money, right? I am saying in terms of the computational requirement, the time requirement. Time requirement for the dynamic analysis is more as compared to the static analysis. So that is why it is not at all necessary that every time you should go for the dynamic analysis. Again, it required more skill, knowledge, and basically the feel for the structural behavior under various types of loading. So if you are having these things, then only you should go for the dynamic analysis. But the most and foremost important thing that you must remember is, if the force is imparting acceleration into your body, then only you should go for the dynamic analysis. Otherwise, you can go for the static analysis. Again, situations in which dynamic loading must be considered. In case of analysis of bridges, because the response of bridge to the moving load, it is very much important. So in this case, you can go for the dynamic analysis. Then action of wind gust, ocean waves, blast pressure on your structure. So if these are the kind of forces acting on your structure, then you should definitely go for the dynamic analysis. Again, a effect of building whose foundation is subjected to earthquake excitation. If your building is in earthquake prone area, then you should definitely go for the dynamic analysis. And if your structure is subjected to a alternating force which is caused by an oscillatory machine, right, then you should go for the dynamic analysis. So these are the situation where you have to go for the dynamic analysis. You cannot rely on the results that you have got from the static analysis. Now when you go for the dynamic analysis, the Newton's laws of motions come into picture, right? The first law, second law and third law. All of us are aware about all these three laws of motion. So I will not read these laws, because these laws we are learning from our school days, right? These are the three laws of Newton's, right? And these three laws are going to govern the dynamic response of our structure, right? So what are the distinctive features of dynamic analysis? Basically, the force is time varying, and the response that we are going to get will also be time varying. So force is varying with respect to time, and the response which is generally measured in terms of displacement, internal forces, stresses, strains are also varying with respect to time. So you will not get a fixed value of displacement at any point. As your force is varying with respect to time, you will get different values of displacement for the same forcing function at a same joint. So a dynamic problem does not have a single solution, but a succession of solutions corresponding to all times of interest in the response history. So look at this figure. This is how your excitation function is, or this is how your force will be applied on your structure. And let us say this is your structure, and what is the response? You will get a response in terms like the graph which is varying with respect to time, because the magnitude of force is varying with respect to time. So the displacement, acceleration, velocity that you will get will also vary with respect to time. And that is why I am saying that you cannot go for the dynamic analysis in all the cases. It requires a huge amount of computational what we can say resources and a time. So you cannot go for the dynamic analysis in simpler structure or where the acceleration is not predominant. But if the acceleration is predominant, you have to do this entire process. Then we have to understand the concept of degrees of freedom. So what is meant by degrees of freedom? We know that the meaning of freedom means the ability to move, right? So the ability to what we can say plot the movement of our structure is given by the term degrees of freedom, right? So what is meant by degrees of freedom? It is the number of independent geometrical coordinates required to completely specify the position of all points on structure at any instant of time. So let us say you have applied some amount of force on your structure. So due to that force, your structure is displaced to some other position. So now you want to find out that new position of your structure. So you will need some coordinates, right? So those geometrical coordinates are called as degrees of freedom. So basically these geometrical coordinates are classified into two different types. One is linear displacement or translational degrees of freedom, and second is angular displacement or rotational degrees of freedom. So we have three coordinate axes, right? We follow the Cartesian coordinate system, and our Cartesian coordinate system has three different axes: x, y, z. So translation or displacement is possible along x, along y, and along z. So we will have three translational degrees of freedom: along x, along y, and along z. Similarly, the rotation of any joint is possible about x-axis, about y-axis, and about z-axis. So similarly, we will have 3 degrees of freedom, 3 degrees of rotational freedoms along the 3 Cartesian coordinate system. So if we consider the total number of degrees of freedom, the total number of degrees of freedom will be 6, 3 along the translational axis and 3 about the rotational axis. So 6 degrees of freedoms are allowed at any joint. So based on the degrees of freedom, we can consider the what we can say the model of our structure. So now whenever we are having a structure, we have to create a mathematical model of it. So creating the mathematical model of it depends upon the degrees of freedom that you are assuming per joint, right? So basically your structure or your mathematical model will be classified into 2 different types. One is lumped mass model, which is depending upon the finite number of degrees of freedom, and another is continuous mass model or distributed mass model, which depends upon the infinite number of degrees of freedom. So these 2 different types we will see in detail later, right? So I hope you understand the concept of degrees of freedom. So now comes the picture of modeling of structure. So how to model your structure, because if you have seen the real time structure is 3-dimensional, it is having length, it is having width, right, it is having depth, but when you have done the analysis, you have just drawn a single line. So how you are drawing a single line when your structure is 3-dimensional? So it is called as the modeling of structure, how to convert your real time structure into some mathematical model. So this process is called as modeling of structure. So first we will try to understand what is meant by lumped mass model or discrete mass model. So the lumped mass model is nothing but where you are lumping your entire mass, right? So the mass of the system is assumed to be concentrated or lumped or localized at various discrete points. So what we are doing, though my column is having weight, though my beam is having weight, though my slab is having weight, I am trying to localize the entire weight of that floor at some point, at some discrete point. And what I am trying to say, this mass is concentrated at that point, and that point is going to displace in x direction, in y direction, in z direction, or it is going to rotate about x, rotate about y, and rotate about z. So I am converting the infinite degrees of freedom into some finite degrees of freedom, and that model is called as lumped mass model, right? So lumped mass model can be categorized as single degrees of freedom, means if your entire structure is having only 1 degree of freedom, then we will call that a single degree of freedom. And if you have localized or if you have lumped the mass of structure at different points, then we are going to call that model as multi degree of freedom model. So let us take the example of this tower, right? So this tower is having different floors. So what I have done in first figure, beside that tower, I can see that there is only one circle, only one mass. So what I have done, I have calculated the entire mass of that structure. I have lumped that entire mass at only one point, and I have considered the entire height of the structure as a single column. So what will be the deflection? The deflection will be only at that mass. So there is only one displacement possible because we are having only one mass. So in that case, I will call this model as single degree of freedom model, because I have idealized that entire structure, I have idealized that entire weight of the structure as a single mass. So if you are modeling your structure, like a single mass, then we will call that structure as, or we will call that mathematical model as single degree of freedom model, right. So now look at the second figure. What I have done, I have lumped the mass of floor, right. One floor at one point, second floor at second point, third floor at third point. So I am lumping the mass at various floor levels. So now mass at first floor will move separately, mass of second floor will move separately, mass of third floor will move separately. So degrees of freedom are multiple. So if you are modeling your structure at multiple points, if you are lumping or if you are localizing the mass at different point, then we are going to call that model as multiple degree of freedom model. So basically lumped mass model is nothing but localizing the mass of your structure. If you are localizing at single point, then we are going to call it as single degree of freedom system. If you are localizing at different points, then we are going to call it as multiple degree of freedom system. So this is your real time structure, and we have, what we have done, we are saying that the entire weight of structure is localized at the slab level, and we have converted into a simple block which is denoting the mass of your structure. Then the stiffness, your column are deforming, so we have tried to calculate the stiffness of my structure, and I have converted the stiffness of structure into a single spring. So this spring and block will give you the displacement of your structure. So converting your actual structure into a spring dashpot model or any a system which can be analyzed easily is called as mathematical modeling of your structure. So this is one part of your model. Another part of your model is also called as distributed model. So what we do in the distributed model, we know that each and every point in your column is going to deform, right. Each and every point on your beam is going to deform, each and every point on your slab is going to deform. Deformation will be different for each and every point of your structure. So if you are trying to consider that each and every point is going to deform separately, it means that your degrees of freedom will be infinite, right. So if your structure, if your mass is distributed along the entire length, then we are going to call that model as distributed mass model or continuous mass model, right. So in this case, mass is considered as uniformly distributed throughout the system, and in reality all the structures have infinite number of degrees of freedom. Using the continuous model you can get better accuracy, but what is the issue with this model? If the degrees of freedom are infinite, then it means that the values of displacement, the values of acceleration, the values of velocity that you are going to get will be infinite, which is very difficult to analyze. But still, with more number of degrees of freedom, we can achieve the better accuracy, right. So these are the two different models which you can used in the structural dynamics. So now in this class, what we have learned, first we have learned why we what we have learned till date, what are the lacunas that we have learned, and why there is a need to learn the dynamics. Then we have tried to understand what is meant by degrees of freedom and how degrees of freedom can be useful in converting your actual structure into some kind of mathematical model which can be analyzed easily, right. So now the next part of the structural dynamics I will cover in next lecture. Thank you.